Okay, so this is lecture number 13. And do you have any questions from the previous class? Anything? So there is one correction which I wanted to tell yesterday, but somehow I forgot. So if you remember that the total integrated noise for the PLL, which I wrote as integral of, this is S total density, which is with respect to F, and I integrated with respect to frequency. So then I wrote that the jitter, so this value will be in radian square, right? Then I wrote actually jitter is equals to one of the, means in terms of, I wrote that this is in terms of, so let me just write as total of f df and integral. This is what I wrote. Okay, and I wrote that the units of this is radian, which is actually wrong. The units of this is in ui, which is unit interval. Is whatever the time period, it is in units of that. Okay, so and here S total is actually equals to S sum of S of I into NTF of I whole square, where I represents like I is the, sorry, where I is the ith noise source. Okay, so yeah, just have that correction, and then the final one which I wrote was right, which was jitter in terms of seconds for a given carrier frequency or for a given output clock is t by 2 pi under root of S total df. And this is actually an RMS value of jitter, root mean square value of jitter. The only thing is this is in terms of ui and the other one is in terms of seconds as per the given clock frequency. Okay, so that goes with the correction. And so I think after yesterday's discussion, I thought I should have one discussion on the jitter as such, what jitter is, and I think that is still confusing. I should have that discussion and show you some real plots and measurement. So just before going that, I will show you a couple of things. So here we have seen that these two things, right? The NTF transfer function of the for the PLL that exists for your charge pump, PFD, resistance, and all those, and the noise densities we have to figure out. This we are going to see after some time. So how does these noise transfer function plots look? So I have something as a plotted. If you see, these are the NTF magnitude response I have. Okay, like NTF of charge pump. So I can't basically write here. So you see NTF of charge pump, NTF of input, NTF of VCO, and NTF of R is a band pass transfer function. The important thing you look here is that NTF of charge pump and NTF of input, right? They both are low pass transfer function, whereas the NTF of the VCO is a high pass transfer function. And these two are related, they are not independent. If you move the low pass bandwidth in, the high pass bandwidth will also move in. So you will be increasing one noise contribution if you are changing the bandwidth with respect to the other. And this is where I said that you need to find an optimum bandwidth for an optimum jitter. Okay, and the next plot will show you. So these are the you can say this is actually the noise spectral densities when multiplied with their NTF functions. Okay, so what you can see for the charge pump, which was a low pass transfer function. So think about it, you are having a low pass transfer function and charge pump noise is a current noise, which is actually constant across all the frequencies, right? So you get SICP out in a red one. Okay, then you have as VCO out. This is an high pass transfer function. It was, but the VCO noise itself is a minus 20 dB per decade at a higher frequency. So you see a falling curve within the VCO. So you do means this is shows you how the S5 out total is combination of all these things. Then what you need to do is you just need to integrate all this blue over the frequency. Okay. So this is just to show you how the plots look like, and these are all plotted with some real numbers. Okay. So any questions on that or on the plots? I think when you do this thing in any given assignment, you will learn how to plot these things. So, pardon? Yeah. So the thing is, so you see, right? This is S5 in, which is which one will be okay? This is C in and ICP. So P in is actually a flat one, and all these noise sources are uncorrelated noise sources. You can add up at one particular frequency, but what you are adding is power. Do not think to add in magnitude and phase, and then you get the right answer. Okay, you are adding these power numbers. Okay, so that just completes the discussion for the discussion for actually the noise transfer functions and the power spectral density. So now I would move on jitter in little bit more detail as compared to yesterday, and we'll tell you different kinds of jitter, what we measure and what is important. Okay, so in a very crude, rough sense, I can say, means if I do not specify what kind of jitter I am using, the yesterday I used like a period jitter and a long-term absolute jitter. If I do not say any such kind of thing, jitter is just you can say measurement or not. It's not a means you measure different kinds of jitter. It's just a performance. It measures performance of a clock. So of a clock, which is timing itself. So this one, so let me plot a little bit to scale. Okay, so if this has been an ideal clock means I am having all periodic event, means I am having periodic events and their period does not change. Okay, so on time axis, this one is 0, t, 2t, 3t. No variation in these edges. That is an ideal clock. Now, if this would have been, means if there is any noise in the system, what happens is your edge moves, this edge can move, and all these things can happen. Okay. So one other thing you can say, let's say if only the first edge moves, I will give you a different kind. If only the first edge moves by delta t amount and the second period is the same, but the second edge would have moved with respect to an absolute time, right? But if on that, if the second edge again adds some plus, then the second edge will move much farther. If it adds a minus, then it may come back to the same rising edge. So the measurement of all these changes with respect to an absolute time is done with different kinds of jitter measurement. Okay, so let me start with this, that there is the first one I would thought is period jitter. I talked about this yesterday also. So period jitter, so let's say I have a clock and I know the mean period of this clock. So you can say two things. That so let me just say uh, this is T1, this one is T2, and so on. So these are the period of the clock in a on an absolute time scale, and I find the mean value of the period that, and whatever is there as a deviation on this mean value, that is measured as a period jitter. Now I can say two things. One thing is, means this I am using, either you can write it, so the mean value of period is nothing but 1 by n of summation of ti I goes 1 to n, right? And you take n large, whatever number you are taking, you take n large numbers, you find the period, mean period. The other thing also I can say, I know the exact frequency of the clock, or I am trying, means if this is coming in a locked system, then locked system means where the frequency is constant. Then I may not even take the mean. I would just say I am using a means I am using a fixed time period TP. This is what I taught yesterday. I said you know the time period of the clock and you are measuring, means I'm not getting this number while doing a mean, but in a sense when you are putting something in a loop, right, the whatever the frequency at the output is actually the average frequency. The things, there will be variation, so either you can measure it or you know beforehand based on your circuit which is generating it, whichever way you want to do it. Okay, now the period jitter is mean square value of t, or time period what you measure. So let me just call as t dash is the time period which you measure with respect to the average time period. So here t dash is time period measured. Okay. Now, yesterday when I told that delta t is equals to ti minus absolute time period, so you can see the t, when you are measuring it, the ti is a random variable. Okay. So when ti is a random variable, delta t of I is also a random variable. So this one is the random variable. Okay, and it can take different values depending on the noise. Okay, so this is same as delta t square. Okay, no, this is time period. So okay, I think that what I used yesterday was same as delta t. So I will say delta t for period jitter is defined in this manner. Okay, I think that will maintain the difference. Okay, so what it means is I, so let's say I measure T1 period and I subtract these. So when I am trying to calculate this period jitter, so I have a clock given to my scope and I measure all the periods. Okay, I find the mean, measure all the periods, and I find the mean period of values, and then I independently I subtracted T1 minus T for each of the clock, and I find the mean square value of that. Okay, that will be the period jitter. But now you see that this period jitter, so this is actually the period jitter is in mean square sense. So if I want, this is, uh, let me just write here, this is in mean square. right? This is not the RMS jitter. The RMS value of period jitter is this. Okay. So this RMS jitter is normally the means the variable which used to identify RMS jitter is sigma. So now the thing is, I know only the sigma value. So I am talking. This is not like I have been given the data and I can do all the annual calculation. I have infinite. I do not have infinite data samples. So all these measurements can be done on a scope only with a finite number of samples. Okay. So now the thing is, I only know the RMS value of the jitter. What can I comment on the peak to peak jitter? Okay. So you know the RMS. So let's say all this is happening in the presence of Gaussian noise, right? That means uh, so means on each of these. Let me just plot here. On each of these rising edges, there is a Gaussian noise, and based on the Gaussian noise, the edge shifts, right? And you know that the Gaussian noise is noise which is unbounded, which is can take an infinite value, but the probability of taking that infinite value is 0. Means close, not 0, but close to 0. So I know only the sigma, but what can I say about peak to peak value of the jitter? How do you know that this is 6 sigma plus minus 3 sigma? How many samples do you need to have for plus minus 3 sigma? Pardon? How do you get the 99.9%? So let's say I want plus minus 5 sigma. Then will it be 1000 or what should be the number be? Hmm. No, I am not. So what you are saying is, let me just rephrase what you are saying. What you say is, I measure for n equals to let's say 1000 samples. So what happens now? So what is the I use 1000 samples. I calculated sigma. Let me just call it as sigma measured. I calculated sigma measured. Okay, then okay. Now I take n equals to 10,000 samples. Then what happens? What do you say much different? How do you fix that number? How does this accuracy come into that defining that number? My question is related to that only. So let me just say that if I want that it's like I want to calculate sigma. I want like something as an error as this thing because I am calculating as per the samples, right? So I cannot calculate any fraction of the samples, right? So what you are saying is that 1 in 1000 of the samples will lie outside the range plus minus 3 sigma if I measure for 1000 samples. The way the measurement is this. Now, what is the accuracy if you go from 1000 to 2000? That surely depends on the measured value. Relation is there for measured value with the number of samples you have measured. Okay, but in order to first say that what confidence you have in your measurement, or like how many samples lie outside the range. For that 99.9% is coming from this probability function itself. So if I just write it what you are saying in words, that let's say the probability of your delta TP is greater than, sorry, lies between k sigma. Okay, so now we know that this delta Tp is having the noise in the system, which is Gaussian, which is like this. So if I say this is minus k sigma and this is plus k sigma, so when I am measuring the number n, right, it will come from here. So I say that whatever I am measuring, what is the probability that the value, whatever I am sampling, that value lies between minus k sigma to plus k sigma. Okay, this probability is, this is equals to 1 by root 2 pi by sigma into 0 to k sigma times exponential of, if everything is Gaussian here, x squared by 2 sigma squared times dx, and this is 2 times of that, right? This thing can be written in terms of your error function or something, which is error function of x by, so let me just write it here. This is error function of x. Let me write it as y. Okay, where y is actually, I think y is actually equals to your k sigma by root 2. You can check this particular ratio. What is like. Okay, now it starts like this. So if I say that I want my samples within plus minus 3 sigma, then I will calculate this value for, okay, probability that delta Tp is less than equals to 3 sigma, that is equals to, oh, this is k by root 2 actually. Error function of 3 by root 2. Okay, and let's say this turns out to be some probability and it actually turns out to be 0.9978 or something, right? Now if I am trying to measure anything in an error, this means I should measure for 3 sigma value, right? If I measure 1000 samples, then I will have 2 in error or 1 in error. Okay, so the same thing holds when you change the number of samples. Let's say I want to have I want my whatever samples I have measured, those error values should lie within plus minus 5 sigma. So I will find for plus minus 5 sigma from this relation that what the probability that it lies between plus minus 5 sigma, which will be somewhere 0.999 something, and then whatever the last number you are having, right, you will see that I should have one addition to that. Okay, if you take lesser samples, then they will be out of the range. Means they will always, if you take lesser samples, then they will always be in range. It's like if I take here 100 samples, right? 100 samples, the probability of 100 samples lying within plus minus 3 sigma is closest to the 1, like is 0.99. Okay, so the way you measure in a scope is when you are measuring how many samples are you going to calculate, that depends on what kind of sigma range are you going to, how much sigma range you want to have, samples you want to have in a system, and you wait for that many samples. Okay, so this is very much the same case when I want to say that I want 1 bit error in 10 power 12, which doesn't come here because it's related, so I'm telling. So let's say I want to have a BER of 10 power minus 12. What that means is I want to have an error 1 in 10 power 12. Okay, now this 1 in 10 power 12 error, you want to know that what kind of, so if I want this kind of bit error, in this case normally we need to find what is k. What kind of noise can actually give me an error of 10 power minus 12. The case in the PLL which we are talking is we want to find the number of samples. Here the number of samples is 10 power 12. You want an error. There the sigma we are saying and say we want to find the number of samples. So the problem is just the other way around. So if you want to find k, this will turn out to be like 7. Something 7 point something. So in order to measure a bit error rate of 10 power minus 12, it's like the noise which can give you that error is in the range is like plus minus 7 sigma kind of noise. Okay. Yeah. Which one? No, I didn't get your point. Hmm. Yeah, 10 power 12 number of samples, and we want to have only one error. You will not have any error. Means if the noise is restricted to plus minus 5 sigma and all the means that is Gaussian and adding in the same manner, you will not have any error. But there the idea is not to find, there the idea is what kind of noise amplitude can affect you. So only when the noise amplitude exceeds 7 sigma, then plus minus 7 sigma, then only you can have an error like 1 in 10 power minus 12. 1 in 10 power 12 actually. Okay. When you say you fix plus minus 5 sigma, what does that mean? You say that the noise is not going to exceed plus minus 5 sigma? Okay. I'm not getting that. Right.
We can observe also.
Yeah.
But we are not fixing, we are fixing K to be 5.
When you say you are fixing K to be 5, what does that mean? That I am asking.
We are fixing the measurement restriction. Yeah.
No, this is not the duration. You can't, because the noise is all present. This is just for the measurement purpose we are using. So what you are saying is there is an, so let me just say, so let's say I have a device under test, okay, and then I add an extra noise to the system and that's what I measure. So how are you fixing the noise in the system? That's the question now.
We are unable to so if we increase you have something like 10 times 10 power
You say, so okay, let me just ask this. I think if I, let's say if BR equals to 10 power minus 9, right? I increase the bit error rate. Then what the K will be? Is that the question? Whether the K is 5 or not is a question, or so. That is what I am saying. That statement is not. So that statement is not. We need K to be 7 is something is not the right statement. So what the statement should be that for bit error rate of 10 power minus 12, the noise mod of noise, or because I'm saying this noise, so let me write it as noise amplitude mod of Vn should be greater than 7 sigma. The statement is this. Okay. So now when the noise amplitude is restricted to 5 sigma, right? Then your bit error rate will actually be much better than 10 power minus 12. So we are not restricting noise anywhere. We are just finding what noise, like what is the range of the noise amplitude. So let me just tell you this. Hmm? Yeah. Yeah, to basically to have, so you can say, uh, Means you are right in the sense that if I want to go from 5 sigma to 7 sigma, to observe from 5 sigma to 7 sigma noise amplitude, I need to measure for more number of bits or more amount of time. Where? Yeah, so this is for Gaussian. I am not adding any deterministic component right here. Which one? Right. So if you have any strong sinusoidal component to it, you need to find what is the peak to peak jitter. It's a deterministic thing. So then when you have the peak to peak jitter, that will affect your period jitter. So that will come as a separate period jitter. Okay. This is only for the random noise calculation. So the whole idea for telling that which means whatever first the idea is, in order to calculate a sigma, you need to wait for a certain number of samples, and when you waited for those number of samples, so let me just get back to the previous point, that I need to wait for 1000 samples to calculate, to have the noise which is present with plus minus 3 sigma. Okay, this 3 sigma is the real sigma RMS value. Now if I know that so let me say, using 1000 samples, I calculated sigma measured. Okay, there is something which is noise present, there is something what I measure. Okay, this is a measured value. This is sigma which is real. Means real in the sense that I'm not affecting what the real value is. Or let me don't write it as real. This is sigma which is present as a noise. Okay. Now the only link which I am having in order to find a peak to peak jitter, so this whole thing is used to find a peak to peak jitter is equals to 6 sigma measure. And this relation I am making only because I am saying when I am measuring for 1000 when I am measuring for 1000 when I am measuring for 1000 samples, the samples are lying within plus minus 3 sigma with the confidence 99.9% or something, and the plus minus 3 sigma peak to peak jitter is equal to this. This is peak to peak jitter plus minus 3 sigma. Okay. But surely this will be in some error with the, because we didn't measure the real sigma yet. We just have certain value of sigma what we measure. Okay. So, and where this period jitter is important, that's yesterday I told one example was where only the duty cycle, means where we are using 2 clocks. So let me just give you, come back to that example. So I have this clock, let's say this is one example, 50. This example I will tell you where I used it. So $590, and I use duty cycle, means I XOR these two things and I get a pulse width modulated or a higher clock. Like this is just the double of the clock, right? This is 50 XOR 590. In cases or in applications where only the duty cycle of the pulse width is important, okay, in those cases your period jitter is important to be known. Okay, it's not the absolute jitter. That, so let me just say, if your period is so if I have a period jitter, what will happen in this case? I will have, let's say, this clock and clock. Okay, So the first clock will be like this, and let's say for the second, the period is the period of the second clock. So I have to vary this one. This is T1, and then I have T2. Sorry, this one is a slightly complicated example, but we use this thing. This is an example which is related to analog mixed signal circuits. Okay, so this one is T2. Okay, so for if T2 period is lesser, okay, then what happens? I have, so let me just mark that part. Just for this, I'm trying to say. So here, the T1 and T2 can differ, okay, but if the only the important part for me is for what time it is high. So this was the one. So let me just mark. Oh, this one is yeah. Okay. So I have new color here. Okay. So this one, these are the for two different periods. I am getting these two different means for two different periods. I am getting these two different XOR outputs. Okay. Now, how much the period jitter is going to change these two things? If both the clock edges move, phi 0 and phi 90, phi 0 is always related to phi 90 with the quadrature of the cycle. And that, for me, that is important. And this is very much in application dependent. And uh, this kind of, so here right now I am having a phi 90. I can change this phi 90 with a certain delay element. So I can get finally a pulse width modulated waveform. Okay, so what that means is if I delay phi 90, what I can get is, let's say, something maybe higher pulse. Okay, this is for one pulse. Then the other one is this. So what matters now to me is if for, okay, let me write it more clearly. This is phi 0 XOR phi 90 delayed. Okay, and okay, this is what I will get depending on the period. Depending on the period, how much this changes. And what is important to me is only this pulse width. So this is used in this kind of pulse width is used in PWM equalization. Okay, this is I'm just throwing this word here. There is something as a time-based equalization where you use this pulse width variation, and there your period jitter becomes. Okay. Now this is for a mixed signal example. Classic example use of digital period jitter is in case of digital blocks. Where so another example is uh, actually your period jitter leads to setup and hold time violations in digital circuits. Okay. This is a more classic example for the period jitter. So let me just say that let's say you are having a D flip flop with a clock, and this is the output. So D is data coming in. Now this one is clock, and let's say the data is okay. This one is data. Okay. Now right now we have a finite means as per the design you have a finite setup time and you have a very large actually hold time, the whole of the cycle itself. Now if my clock edge moves, I will violate the setup time. Okay. And if my so the thing is here, let me, if the data this is too high, so let me just like there's too slow data, so that will not show you hold time violation. So this color coming. Okay, you can say this one is used in a serialization case. So if my edge moves the other way, then I will have a hold time violation. T hold time violation. T. It is more like the period. It's dependent on the page. So period jitter is like if this edge moves, then the next edge, how much that's the next edge moves. Period moves itself. Any questions? Period jitter is when you say a long-term phenomena, it is means long-term phenomena. You are saying just because we are calculating for long-term? No. So a long-term phenomena in jitter is something means that is called something different. So period jitter is not a long-term phenomena in the sense that the jitter is getting accumulated. Okay, in non in regular when we define jitter with respect to clock or something, the long-term phenomena is I will show you what the difference is. So let's say I'm having a clock. This is what actually I started with, and I add. So let me start marking. I add delta t here, right? Now for the next rising edge, previous delta t was there, right? Means this was already there if the next edge didn't have any added noise. But then I went and added another noise. Now for the third edge, the first one is there, the second one is there, and if I add any noise, then the third one is there. Okay, so this noise keeps on getting accumulated unless you go and reset or do something. So this kind of jitter accumulation, uh, like this is one cycle, this is second cycle, this is third cycle. If you keep on looking with respect to absolute time, so what is my absolute time? My absolute time is, I'm just saying, my absolute time is still the same rising edges. What? Sorry. So you can say the new rising edges. Let me plot the new rising edge for this will be here. It is here and here, right? So with respect to the ideal rising edge, the new rising edge keeps on moving. That is accumulating the jitter. If you have do not have any feedback loop in the system, you are observing such a clock, you will find that the jitter keeps on accumulating and may even, with respect to absolute, may even, it's this an unbounded thing. It will just keep on increasing. This is a long-term, this is called as a long-term accumulated jitter. Okay, now, so let me say this leads to your long-term accumulated jitter. Long-term accumulated jitter. Okay. Now the next case is the period jitter which we observe over more number of cycles. Okay. Now, if the clock frequency, so let me just say, let's say this is the clock. Okay. So in long term accumulation, this is giving me 0. But the period, if you see, the period of the second clock is much different from the both the sides. And if suppose I have all the setup and hold time for this kind of clock, and if I get the next clock cycle is this, it is highly likely it will violate the setup and hold time violation for any digital synchronized circuits. A strong noise of FF by? Yeah. Period jitter will be much higher. Means I have shown you as a very deterministic sense, but so the thing is, in a long, if you are talking of some clock circuit which is not in any feedback loop, okay, then the long-term jitter is going to be crazy. Can be. So I put can be there means it's like how fast the things are getting corrected, how slow the things are getting corrected. That will depend on that. Okay, but here the whole logic is to see where this period jitter is more important. As so in digital logic, it is more important, right? Whereas in case of your the long term absolute jitter is the absolute changing in the system. Absolute time changing, and I think for that I give an example of a clock and data recovery loop. If you keep on shifting the clock, then and you're looking for a bit at a rate of 10 power minus 12, you will surely hit that thing. Okay, so the next jitter which is defined is cycle to cycle jitter. Okay, and what it is, cycle to cycle jitter is this one is t of I time period, and this one is t of I plus 1. Okay, and so on. Now, delta t cycle to cycle of I is defined as t of I minus t of I minus 1, or you can write t of I plus 1 minus t of I. So, this one defines the difference between the two adjacent time periods. Okay, and the same statistics will follow that what is, so you measure it over how many number of cycles. Okay, and normally the cycle to cycle jitter is defined in terms of peak to peak. You measure what is the difference between two adjacent clock cycles, you measure over number of samples, and what's the main peak to peak jitter. It's mostly used as peak to peak, lesser as an RMS. Okay, so now if I define cycle to cycle peak, cycle to cycle jitter is equals to max of t of I minus t of I minus 1, where I is basically less than equal to whatever the number of I is just 1, 2, 3, whatever number of samples you measure. And in normal standards, you use like 10,000 clock periods, 10,000 such values are used, or 10,000 samples are taken for measuring cycle to cycle jitter. Okay. Now, why do we use cycle to cycle jitter and not period jitter, or what's the difference between the two? So both of these things. So now, if I am telling you that this is the difference between the two adjacent cycles, then this is surely doing the same thing, setup and hold time violations as in the digital logic, right? And why is it more important as compared to period, or what's the difference between this and the period jitter, other than the numerical difference which we have seen? So for that, the thing is, when you are having a spread spectrum clocking, okay, so there is something called as spread spectrum clocking. Okay, what that means, what clocking that is, that in a regular or in an ideal clock, there will be only one tone, ideal clock. Okay, so whatever it is, FC, this is the spectrum of an ideal clock. Whereas for a spread spectrum clocking, you will have some kind of variation. The whole clock power is not in one particular tone, but the clock is varying. And what kind of, whether you are varying the, so here the thing is, in time domain, you actually vary the clock frequency. So if I, so for ideal clock, I am plotting this as a frequency. Okay, for ideal clock, frequency is constant. For spread spectrum clocking, this is one example. For spread spectrum clocking, you can have, sorry, so FC minus delta, FC plus delta, and in between. Okay, this is also frequency. This is for spread spectrum clocking. Okay, and this kind of clocking is used in to reduce the power concentration in one, and it's used in CPUs at many places. Okay, now when you are measuring a period jitter, think about it. When you are measuring a period jitter in a, for a spread spectrum clocking, that is much susceptible now, because the frequency is varying all over. So what you will do, you will find FC as a mean period if you take n number of samples, and the jitter is now getting very large. Okay, but for cycle to cycle, the value is not changing that continuously. So cycle to cycle jitter is much more gives about the information about the stability of this spread spectrum clock, whereas the period jitter is much susceptible to the spread spectrum clock, the values. Okay, that is the place where you use a cycle to cycle jitter. Okay, so let's stop here. We will continue in the evening.